going to start the lecture on advanced reaction engineering. In this lecture, we will discuss about moving bed reactors and catalyst deactivations. So, in our previous class, we already have discussed about the catalyst deactivations. So, when there is a catalyst we are using for a particular reactions. So, in particularly the gas and solid reactions, catalyst is the solid and the reactant that may be vapor phase or gas phase, they come in contact and react. Then during reactions various way catalyst may deactivate, that may be due to the coke depositions or maybe catalyst sintering or maybe catalyst due to the poisonous component that may be get adsorbed over the surface of the catalyst. So, once it is get adsorbed or agglomerations is there or coking or coke deposition is there, catalyst deactivations is there. So, therefore, what would happen, the catalyst, once catalyst is deactivated means at the beginning of the reactions that performance of the reactor catalyst or the systems would be very good, but with progress of the times and progress of the reactions, the catalyst deactivation is there, slowly it is deactivated, activity gradually downing, then the overall conversions rate everything should be decrease conversions. So, therefore, various type of reactors we already have discussed, packed bed reactors. So, here today we will discuss the moving bed reactors. This is one of the reactors. So, here catalyst would be taken inside of the reactors, but the in the form of bed. Okay. So, that bed would move at a particular flow rate, so or particular velocity. So, that would move during reactions, means catalyst would be charged inside of the reactor, but movements would be there with the reactant that is the feed that would be charged. At the same times the catalyst bed also would be moved through this reactor, then both reactants and the catalyst come in contact, then reactions will take place at that particular temperatures, and then desired product formations would be there. At the same times catalyst deactivations also would be there, means two reactions would be there, catalyst deactivations as well as reactant A that would be converted into the product, both the reactions will take place simultaneously. So, in that case or in the moving bed reactors, so how the conversions will vary along the weight of the catalyst or activity that will decrease. So, that part we will discuss basically. So, now the loss of activity of catalyst when we are taking a catalyst for a particular cracking reactions, they are hydrocarbons, basically higher molecular weight hydrocarbons, that is the gas oil, heavier fractionates from the petroleum crude, that is usually cracked. So, when that cracking reactions will take place, the deactivations may be various type that already have discussed, that may be slow decay, means activity of the catalyst, that may be slow decay or may be moderate decay or may be rapid decay. So, today that we will discuss basically the temperature time trajectories or the slow decay, that part we have discussed in our previous class. So, today we will consider moving bed reactors, and here catalyst deactivations is there, but that is moderate, not very high or not very slow, means the catalyst deactivation is not very fast, not very slow. In that cases we can consider moving bed reactors for that particular system to operate it. So, once in most of the cases when the catalyst deactivations is there, so it is required catalyst regenerations. Why this type of moving bed reactors or straight through transport reactors, these are the reactors or fluidized bed reactors are required. It is basically when the catalyst deactivations is there. So, there may be a stipulated time, maybe 30 minutes, 1 hour, 20 minutes, we can put that particular catalyst inside the reactors. Within that period of times, that catalyst will take part in the reactions, okay, with that will interact with the reactants and conversions will take place. After that we have to take out the catalyst from the system of the reactor, and then fresh catalyst will be charged simultaneously, both the things will be done simultaneously. So, as a result what would happen, the catalyst, spent catalyst or deactivated catalyst, so that would have to send to the regeneration units. There is a regeneration unit for the catalyst regenerations or replacement of the catalyst, means this is simultaneously also will take place, means once we have a fresh catalyst here, let us say this is a fresh catalyst, we have charged A reactants, continuously we are getting B as a product. But when this catalyst will be deactivated, we have to take out this catalyst from the reactors and fresh catalyst we have to charge inside of the reactors, and spent catalyst or deactivated catalyst we have to take out from the system. So, by that way we can maintain the process, means the reactions we can maintain at a fixed rate or fixed conversions, the desired conversions always we need, that we can maintain that way. So, otherwise conversions will be down, then overall others means associated part of that total systems, means in the process, that may be separations or maybe other parts, integrated parts are there, so the rest of the part would be affected. So, therefore, to maintain a constant conversions of that particular reactant, so we have to always take out the samples or catalyst from the reactor. So, this is the typical design of a moving bed reactor, that already have discussed this type of reactor. Here this is the reactor part, this is the yellow portion, this part is the reactor. So, here the reactant whatever we have that would be charged, that would come inside of that feed point, that is the reactant. If we have a, let us say this is the reactions, we have a cracking reactions, let us say petroleum fractions of gaseous oils that we want to crack into gasolines or lighter components. So, then A will be charged from here, and then catalyst would be charged from here, fresh catalyst will be charged here. So, here catalyst would be here, and at the same time reactants would be there. So, both would be take part in the reactions at a desired temperatures, let us say 450 or 500 degree centigrade we have to maintain here, let us say 500 degree centigrades we are doing the cracking reactions. So, we are maintaining temperature, reactions will take place, then corresponding the product that would come out from here. So, then so what would happen with the catalyst? The catalyst would be deactivated, its activity gradually decrease, the catalyst will be take out from here, it would be come here in the kiln. So, this is the kiln or the furnace, here also we have to maintain some temperatures, this is reactor part and this is furnace you can say. So, here is the spent catalyst, that part would be here spent catalyst or the deactivated catalyst, the catalyst deactivation is not at the beginning or the fresh catalyst. So, then that catalyst would be here spent catalyst, and see here air or oxygens that would be fit in this part in the furnace. So, here at a desired temperatures in presence of oxygens or air, that deactivated catalyst would be regenerated. This is basically the regeneration unit. See here, once it is regenerated, the against that spent catalyst in the form of fresh, that would be again sent back to here. This is the lift out, lift from here the excess air that would be go out from the system. See here catalyst and air would be separated out, this is basically separator. So, here the fresh catalyst will get here at this particular location. So, then again that fresh catalyst that would be entered into the reactor, that will the systems will automatically will run throughout, maybe 1 day, 2 days, 3 days, 30 days operations, 1 year operations, that way systems will continuously operate. That way actually the continuous operations of the systems that usually work in a industrial scale. So, here if we look into this catalyst or this reactor part, here I have designed actually this is the bed of the catalyst, that is not small particles we are taking in the form of bed, that catalyst bed was taken, this is the catalyst bed, it has a particular movement or velocity, this is the reactors let us say, it has a particular dimensions x and y or diameters, if it is spherical cylindrical. So, then it has a specified diameter and length is also there, that catalyst bed would come here, this is the reactors, it is moved at a particular velocity, it may be 10 kg per second or 20 kg per second, that catalyst movement rate. So, that would here and reactant is here. So, this part actually the reactor part we are showing here, catalyst bed is entered inside of the reactors and after that the spent catalyst is leaving out from the reactor. So, it is the bed of the catalyst is not fixed, here movement is there. So, moving gradually, but at a slowly but steadily, and there a movement is there always. with the reactants is coming, and like that product maybe here we will get. So, here the fresh catalyst, let us say the total amount of the weight if you want to know. So, then we can multiply it with the density, cross section area, and if the know the total length of the this reactor, inside of the reactor total height or jet length if we know, then total fresh catalyst that was used, that we can calculate easily using by knowing the density of the bed, cross section area and z. So, if we multiply that. So, this is the moving bed reactor. So, here this type of catalyst details we have discussed. So, now the detail how the systems or the reactor operates, that here we have means point by point we have shown here. So, fresh catalyst enters at the top of the reactors and moves through the reactors, and then catalyst cooked continuously as it moves through the reactors to the downs, means reactions would be there, and then from the end or the exit of the reactors that spent catalyst would be come out from the reactors, and that would be sent to the kiln or the furnace, and there air is used to burn off the carbons, that is the coke that usually deposited over the surface. So, and then generated fresh catalyst would be lifted and sent back to the separators, and then from there to the reactors. By that way systems will operate. So, now we have to develop a material balance equation or design equation for this particular moving bed reactors, as if we can calculate. So, at the particular velocity or particular movements of catalyst bed is there. So, what would be the movement rates, what would be the conversions, what would be the catalyst weights, everything details we means want to get for this type of particular reactors. So, here is the material balance for these reactors by considering a delta W amount of the catalyst within a delta Z length we have for that particular systems. Here let us say here W, and at this particular point here weight is the W plus delta W, and at this location is Z, and at this particular location is Z plus delta Z. So, at delta Z locations catalyst weight is W, Z plus delta Z location the catalyst weight is this. So, within very small fraction of changes of catalyst weight, if we do the material balance for this particular components A with respect to component A, molar flow rates of A with at W that particular point or location when W amount of the catalyst was there, molar flow rates of out of that particular component or reactant A. So, that is at this particular location W plus delta W, within that outer means after the reaction. So, that molar flow rate of component would be this is inlet flow rate, this is outlet, and this is the rate of generation part R A prime, that is the rate of generations for component A per unit weight of the catalyst per unit time. Here if we total weight of the catalyst that we have taken, that was delta W, within that the rate of generations that we are conducting, and at steady state accumulation part this part would be 0. So, therefore, this is the general material balance. If we divide both side, left hand side and right hand side with the delta W, and taking delta W tends to 0. So, then the final equations would be this. This is the differential form of design equation for this moving bed reactors. So, here's now rate of reactions at any time, since the rate of reactions means catalyst is going to deactivate with the times progress of the times. So, then R A minus R A prime, that is the rate of the reactions at a that particular reactors for that particular component reactant A. So, this is the activity terms, and this is at the beginning the rate when catalyst is the phase, catalyst was the phase that was charged inside of the reactors at the time t equal to 0. Then so this activity component and this rate part we have to put, means reactions rate constant and concentration of individual components. So, this is the rate term but basically, and this is the deactivation terms or activity terms of that particular system. So, now these are the two terms we have to find out for a specified, means if you know the rate of the reactions for the reactions we are going to conduct in a moving bed reactors, and if you know the activity or deactivations rate or deactivations kinetics for this particular system. So, then both we can put it here, and then the overall rate for the systems we can know, and then in the design equation that we can replace. By that way we can simplify the equations, and the design equations will get in the form of differential form that we can solve in a differential ordinary differential equation solvers. By that way we can, if we means that components or the parameters are required, everything are known, then we can solve it. So, now in the activity terms for the catalyst, let us say the decay rate law for this particular systems or in the moving bed reactors where catalyst is going to deactivate. So, the deactivation rate we can write, this is the general deactivation rate equations minus dA by dt, that is equals to Kd into a to the power n. Here the deactivations order of the reactions, deactivations equations, that is the nth order, and Kd, that is the deactivations rate constants that we can write. So, that already we have discussed in our previous class. So, now this equation we have to simplify. So, how we have to do that we will discuss. Now, see here, so when that catalyst is moving or coming here in the right hand side, catalyst bed is there, this is the reactors and this is the catalyst bed or catalyst bed that is moving inside of the reactors. So, if a particular velocity that is moved, so means how long the catalyst remain inside of the reactors or how much time that catalyst spend inside of the reactor for the reactions. So, reactants also is moving, means entering and leaving from the reactors, and catalyst also in the form of a bed that is moving and leaving from the reactors. Therefore, if we know the totals, let us say W amount of the catalyst was there, total weight of the catalyst inside of the reactors, that maximum amount, let us say W amount, and that velocity of that or movements of the catalyst, let us say the US, that may be a particular kg per second or kg per hours, let us say 10 kg per hours catalyst movement rate. So, if W amount of the catalyst and movement rate is this, so then amount of the times we will get, that is the contact time, means the times catalyst and reactants, means A is the reactants that we are getting, this is the catalyst. So, catalyst and these reactants take part in the reactions, means for that particular stipulated times they will be remain inside of the reactors, means reactants as well as the catalyst, the within that contact times they will be there inside of the reactors, and during that period of times the reactions will take place, at the same time catalyst deactivations also would be there. So, these equations we can write in the differential forms. So, we can write dt equals to dw by us, us is the constant, but weight is the different changing along the length of the reactors. So, dt equals to dw by us. So, now this we can substitute in the this equation, this decay rate law, this here we can substitute in equation 4, we are substituting dt part, this dt part we are getting. So, this we are substituting, then we will get minus dA by dw equals to Kd by us A n. So, now this is the catalytic catalyst deactivations rate law or activity catalyst activity equations. Okay. So, equation 5 is the catalyst activity equations. So, now from the design equations for this particular mole balance equations we have derived. So, in the mole balance equations, this is the mole balance equation or the design equations, here minus R A primes we know. So, R A primes we have to substitute here, R A prime equals to minus R A prime equals to activity into this is the fresh catalyst rate. So, here these equations, this is the design from the this is for design equations for that particular reactor, and this is catalyst deactivations or activity equations. Okay. So, this equation is coming from the catalyst deactivation and this equation from the design equation for this particular reactors mole balance equations or design equations. So, here this activity and this is the rate. So, these equations we can simplify or we can write this way. Okay. So, dx by dw is there, that would we are keeping it in the left hand side, and F A naught we are putting in the right hand sides. So, this is the basically the design equation for moving bed reactor, these equations. So, now we have equation 5 and equation 6, both are in the form of differential form of equations. So, these two equations if we want to solve, first we have to know small n value, Kd value, Us value, and similarly F A naught value we have to know. So, these are the components if you know. At the same time for this rate of the reactions, means if the reactions is let us say first order rate equation, second order rate kinetics, or maybe non elementary reactions, the rate if we know. So, then these are the components we must put it here in the equation 6, simultaneously these are the equations we can solve, we can get, otherwise See here we are assuming that for a case first order decay rate law means we are means here the equation 5 was n, what would be the n value that we do not know, in case for a case n equals to 1 we are assuming, and then the equations will be simplified for the first order decay rate law. After integrating these equations we can get it, means from these equations if we do integrate by rearranging, here dA is there, this is A is there, dW we can put in the right hand side, means we can write this equation this kd us into dW, this way we can rearrange this equation. After that we can integrate this equation, after integrating with that boundary conditions we can get A equals to this. So, here this is the activity in terms of catalyst weight and velocity or movement of the catalyst bed. So, we know concentrations as a function of C naught into x, this way you can write, and this is the rate equations for this particular reactions rate. This is not deactivation rate, this is reactions rate. So, reactions rate we can write, this is a, let us say for example, it is a second order reactions, then reactions rate constant we know, and the concentrations of that component A. Here so this Ca we can put it here. So, then this minus R A prime, that is the rate. So, we can put this, see here this is the activity terms and this is rate terms. So, this A t and minus R A prime, these are the two components we need, component 1 and component 2. So, these are the two components we can substitute here in equation 6. So, A t we can substitute, minus R A primes we can substitute. So, once we substitute, then dx by dw, the design equations would be in these forms. Okay. So, by considering these equations we are integrating deactivation equations, then we are getting this equation 7. From equation 5 after integrations or simplifications we are getting equation 7, and rate equations after simplification or putting these are the components we are getting this. So, this is the design equation for that moving bed reactor, considering deactivations rate constants, reaction rate constant, catalyst weight, movement of the catalyst or velocity, and initial concentration of the reactants if we know, molar flow rates of that component A we know. These are the component value we can put or we can provide. This is the dx by dw is that differential form of conversions and weight of the catalyst, how they are related with right hand side. So, if let us say we need 60% conversions, so then either we can integrate this, then we can know how much catalyst is required for a desired conversion, that we can find out, or that or else we can do, we can use this in a ordinary differential solvers. So, once we use this equation in ordinary differential solvers, there's means the known components, these are the known components, means Kd for deactivations rate constant, that is it has a particular value, reactions rate constant for the reactions rate constant, that is has a value. So, these are the components if you know, Ca naught, that is the initial concentration of the reactants, weight of the catalyst means that would vary, Us if the movement of the catalyst beds I said 10 kg per second we have considered, that may be instead of 10 kg it may be 5 kg per second or maybe 2 kg per second, that way also maybe, that depending upon that particular systems or the operations we are going to conduct or we are going to study. Okay. So, depending upon that it may vary also. Okay. So, if we consider a specified movement of that bed, so these are the components we have to provide, and F A naught equals to V naught into C A naught. So, C A naught is known. So, V naught is also known, means volumetric flow rates, and this is the concentration if you know, then molar feed rate, mole per unit times we know. So, these are the components we have to provide to solve these equations. Okay. So, either equation 10 we can separately solve, or this equation 5 or equation 6 simultaneously we can solve in a differential solver by providing all the components or the terms. So, then we will get from the outputs, we will get x versus w will get x equal to 0, 0.1, 0.2, 0.3 like that, 0.5, 0.6, 0.8, 1 up to this we will get. So, here 0, 1 kg, 2 kg, 5 kg, 10 kg like that, this would come, that is would come after solving these equations, equation 10 if we solve. So, then this will get, this value will get. If we plot them, also there is activity terms is also comes. So, here also some value would be there. So, with changes of the weight or the conversions, activity terms also will be there. So, if we plot conversions versus W, so the natures of the curves would be like this, means along the changing of the weights of the catalyst, the conversions would vary like this, and at the same time since the catalyst is going to deactivate. So, with the progress of the reactions and movement of the catalyst, so then the activity terms also would be like this, this is the activity terms. Okay. So, activity of that catalyst means at the beginning activity was very good, means rate at that particular times, and 0 time means fresh catalyst, means used catalyst, and activity usually we express R A primes t equals to t times by minus R A prime t equal to 0. This is the rate. So, this is the activity. So, activity gradually will decrease. So, that is happening here. So, this curves will get. So, from here we can say that when a moving bed reactors we are doing any cracking reactions or any particular crude oil crackings, and the catalyst is moderately deactivated, not very fast deactivating or not very slowly deactivating. So, in that case we can develop the design equations for the moving bed reactors, and we can solve the moving bed reactor design equation by considering material balance equation, at the same time catalyst deactivations rate equations. So, this equation is very crucial or important. So, this here we have not put in the pressure drop term, means that term also you can put. So, that also you can solve as we did by considering the argon equation also similarly, but here we are not considering, there is no pressure drop in the system. So, only just how the conversions is varying with the weight of the catalyst. So, this means data or graph is very important for the moving bed reactors, and at the same time so these are the design equations when the catalyst is going to deactivate, moderately deactivating. Okay. So, you should means keep in mind that when temperature time trajectories is required, when the catalyst deactivation, in all these 3 cases catalyst deactivating, but the catalyst deactivation is very slow, then temperature time trajectories we should follow when catalyst deactivates moderately, not very fast, not slow. So, then in that case moving bed reactor we can use. Okay. So, in the next class we will discuss about when catalyst is rapid deactivation is there. In this case straight through transport reactors is useful, STTR. So, that reactors we will study. So, then how to design that reactors, and similarly in that case also catalyst deactivation is there, but we will develop the design equations, and by considering any numerical problems we can solve that. Okay. So, thank you. So, today is up to this.